Hello and welcome to the last video on our topic, which is now natural convection, or also known as thermal convection. So this topic links a bit with what we have done in topic 2 in convection processes. But in this case, we're gonna be analyzing a new phenomenon. So as you can see here now, when you are using, for instance, a barbecue, you can observe that sort of turbulent flow over the grill. Why is that? So what's happening there is that there is a massive temperature difference between the surface, so between the grill surface, and the temperature of the air. So because you have this massive temperature gradient there, that driving force, right? That automatically induces a change in the air density, right? So the air which is closer to the grill is going to be at a much higher temperature, and therefore at a much that's going to have a much lower density. So because of this temperature gradient inducing a difference in densities for the air, you have what it's called a natural convection process. So you have a fluid flow. The air is moving based only on density differences. So in this case, for natural or thermal convection, the velocity of the fluid again is zero at the heated body, at the surface. As you remember, that's called the non-slip boundary condition. But this velocity increases rapidly in a thin boundary layer which is close, or which is over the heated body, and again it becomes zero again far from the body. All right, so what we're seeing here is a fluid flow which is induced again by a temperature difference, not by pressure differences or external work, as we analyzed in topic number 2 in convection, in heat transport and mass transport by convection. Now, for analyzing natural convection processes, it's quite useful to define a new parameter, beta, which is the coefficient for volume expansion. And basically what this coefficient of volume expansion calculates or give us an idea about is on how the volume of, or the specific volume or the density of a material changes over temperature ranges, right? So this is a thermal property that you can find either tabulated for liquids and gases, or you can actually calculate it very easily, only in the case of gases though, by just calculating 1 divided by the absolute temperature of the process. So I don't expect you to memorize this definition, but we are going to be using, just be aware of this coefficient of volume expansion, because we are going to be using it to estimate other important parameters. Now, from a microscopic point of view, if you remember, the way you calculate or you compute velocities or fluid velocities is by solving the Navier-Stokes equation, which is just a more complex version though, of the second Newton's law for fluids. And in this case, how do we accommodate the natural convection term? Well, in this case, if you have a look at the original Navier-Stokes equation, there was a density or a times gravity term. So that's basically the hydrostatics. So how a fluid moves through by hydrostatic forces. In natural convection, that hydrostatic term is related then to temperature, as you can see in the last term of the Navier-Stokes equation. So it's gravity times that beta coefficient, the coefficient of volume expansion, times a temperature difference between the fluid and the far-field fluid. And obviously this very complex differential equation has to be solved together with the heat conservation equation. So temperature is the parameter linking the fluid flow equation, so Navier-Stokes, and the heat conservation equation. At this stage, I'm not going to ask you to solve both differential equations together, because that's beyond the scope of this module from a mathematical point of view. But what I want you to remember is a basic concept. So you have temperature differences that are inducing changes in densities and therefore inducing a fluid flow with a specific velocity. The same theory about boundary layers apply to natural convection. So if you remember, for convective processes, you have a fluid flow boundary layer over a surface and a thermal boundary layer through which you have a temperature gradient. That's when you have a fluid flow, so forced convection. In the case of natural convection, you don't have forced flow, right? So the velocity of the fluid in the far field is zero. In thermal convection, it's a stagnant fluid. However, still you have a boundary layer for the fluid flow, and you have a thermal boundary layer across between the surface and the fluid, right? So once again, we're gonna be looking at how we can calculate the thickness of such a boundary layer for natural convection. Why? Because this is gonna tell us how efficient the heat transport by natural convection is. The mathematical treatment is exactly the same as for forced convection. So how efficient the heat transfer by natural convection is between a solid surface and a fluid? Well, it depends again on the thickness of the thermal boundary layer. So the local heat transfer flux J. So the physics is the same, is exactly the same. We are going to then think about, all right, how do I calculate this H, heat transfer coefficient, for natural convection? So in the same way as you use different correlations, empirical correlations for convection, for forced convection, by relating the Nusselt number to the Reynolds number and the Prandtl number, if you remember, for natural convection, we have something which is pretty similar. So we have the Nusselt number again, which is the heat transfer coefficient H times L, a characteristic length divided by the thermal conductivity of the fluid, K. So that's calculating the Nusselt number. We'll be able to find out what H is. But this time, for natural convection, you don't really use the Reynolds number. What you use is a new dimensionless number that I am sure you haven't seen before. It's the Grashof number, GR. And again, we find the Prandtl number here. Remember that I don't want you to memorize how to calculate every single dimensionless number, all right? So what is this Grashof number, this new dimensionless number? Well, in the same way that the Reynolds number relates inertial forces to viscous forces, the Grashof number relates something different, which are the buoyancy forces to the viscous forces. Why is that? Because during a natural convection process, you have buoyancy forces, or in other ways, differences in density. So obviously, for very large Grashof numbers, so orders of magnitude much larger than 1, that means that the buoyancy effects are really important compared to the viscous forces. Now, the Grashof number can be calculated using that expression I'm giving you there, gravity, so 9.8 meters per second squared, beta, the coefficient of volume expansion, times the temperature difference between the surface and the fluid, times a characteristic length to the third power, divided by the kinematic viscosity squared. An extremely important thing you have to remember here, when you evaluate the properties using a natural convection correlation, when you evaluate what the kinematic viscosity is or what the Prandtl number is, they have to evaluate it at the film temperature. That means the temperature, the average temperature across the boundary layer. What is that film temperature? Well, it's just the average temperature between the surface temperature and the fluid flow temperature. So first of all, you calculate that film temperature, and then you find what the viscosity, the density, and the Prandtl number are at that temperature. Remember that for forced convection, we did something a bit different. We evaluated the thermal properties or physical transport properties like viscosity, thermal diffusivity, density at the bulk fluid temperature. However, for natural convection, you will have to use the film temperature to evaluate those transport and thermochemical properties. Now, a boundary layer in a natural convection process, it can be either laminar or turbulent flow. in the same way as for convective forced convection processes. However, you cannot use the Reynolds number to evaluate whether the boundary layer is laminar or turbulent in natural convection. Instead, you have to use a new dimensionless number, which is called the Rayleigh number, and it's just obtained by multiplying the Grashof number times the Brandt number. And the rule of thumb is that if the Rayleigh number is larger than 10 to the 9, that means that the flow is turbulent. If it's lower, it's laminar flow. Okay? So Rayleigh number, just to know when the fluid flow is laminar or turbulent, nothing else. Very simple. And finally, it's quite common that in practice, natural convection and forced convection, so natural convection is what we are studying now, topic 3, and forced convection is what we studied in topic 2, in the previous topic. In practice, natural convection and forced convection, they occur simultaneously at the same time. Sometimes, however, one of the mechanisms is much more significant than the other. So sometimes you could describe the whole process by a natural convection process. Sometimes you can describe the whole heat transport process by using a forced convection process. Sometimes both natural and forced convection processes take place in a significant way. Again, this is a rule of thumb. To determine whether the natural or forced convection is more significant upon the heat transport process, what you can do is to calculate a new dimensionless number, which is just dividing the Grashof number by the square of the Reynolds number. And in terms, what is the physical meaning of the Grashof number divided by the square of the Reynolds numbers? It gives you an idea about the ratio between the buoyancy forces and the inertia forces. What does this mean? This means that if the Grashof divided by the square of the Reynolds is much, much larger than 1, that means that the buoyancy term is much more significant than the inertia terms. Or in other words, buoyancy is more important, therefore natural convection is dominating the process. On the other hand, if the ratio between the Grashof number and the square of the Reynolds is much, much smaller than 1, that means that the inertia terms are much more significant than the buoyancy terms. And therefore, in that case, what you have is that the forced convection is dominating the heat transport process rather than the natural convection. So that's all. Thank you.